Welcome back to Hardware Security. This time we're going to learn hardware Trojans and trusted integrated circuits. From this title, you know that we're going to cover both hardware Trojans and trusted integrated circuits. For hardware Trojan, we're going to give the definition of hardware Trojans, and we're going to study the taxonomy of hardware Trojan. It is very important to do such study because instead of study dozens or hundreds of different hardware Trojans, we can focus on several different categories. And within each category, we can study the similarities between different hardware Trojans. We can capture their physical characteristics, and we can develop benchmarks to do the testing. And more important, we can develop hardware Trojan detection mechanisms. For trusted integrated circuits, we're going to give the definition of trusted integrated circuits. We're going to talk about how to build trust in integrated circuits design. In particular, we're going to talk about how to prevent hardware Trojan insertion. We do need a lot of background to understand this material. Start from the traditional digital logical design to crypto algorithms, and in some extent, including the digital watermarking and fingerprint techniques we have discussed earlier. However, the good news is, since you are all here, you are in a very good shape to proceed and learn this very exciting material. Hardware Trojans, they are any additions or modifications to a system or to a circuit for malicious intentions. So from this very simple definition, we can see two characteristics of a hardware Trojan. First, a hardware Trojan must have malicious goals. And the most common malicious goals for hardware Trojan includes trying to change the circuit's functionality, trying to control the system, or trying to steal sensitive information such as secret key from the system. Also, some of the hardware Trojans, they are trying to reduce the circuit's reliability. And by doing this, a system will start malfunctioning before its lifetime expires. Also from the definition, we know that a hardware Trojan must be added or modified intentionally. So this basically tells us, for example, the traditional designs, we have a lot of don't cares. And we have discussed earlier, so we can introduce a lot of backdoors as security vulnerabilities during the design. These are not intentionally introduced into the system, so they are not considered as hardware Trojans. And also, we talk about a scan chain, which is part of the testing circuitry. These are intentionally added to the system, but they're not added for malicious purpose. So scan chain are not hardware Trojan as well. Trusted integrated circuits, on the other hand, is a system or is an integrated circuit that does exactly what is asked to do, no more and no less. It is a very simple definition, but it is really very hard to assess the trustworthiness of an integrated circuit from this definition. So let's start with several examples of the system which are not trusted. So first, if a system fails to deliver certain required functionalities, such circuits or such system cannot be trusted. And second, if a system has hardware Trojan inside it, this system cannot be trusted either, because this system does something more, and these things are malicious hardware Trojans. So from this definition, we want to ask the question, so does such trusted integrated circuits really exist? As we have seen the traditional digital logical design, when we specify the systems, normally we have a lot of don't cares. Even if you fully specify the system, during the design process, you may introduce some internal don't care conditions, such as the satisfiability don't cares or the observability don't cares we have discussed earlier. So with these don't cares, and the system is going to give some deterministic values for the don't care conditions. And those are not specified, so whenever they have any deterministic values, they will be considered as more to the system spec. So in that sense, my argument here is such trusted integrated circuits following this definition does not exist. So this brings us to, in some sense, my definition of a trusted integrated circuit. So first of all, it must satisfy this condition, no less. So for all the required functionalities, all the required specifications, the system or the circuit has to satisfy those. And second, instead of no more, we define this trusted IC to be, it doesn't do any malicious more. So in some sense, if we know all the possible attacks or all the possible vulnerabilities or all the possible bad intentions that the attacker can put into the system, if you can verify none of these things exist in the system, then the IC can be considered as trusted. So let's start with a small example to show what do we mean by trusted ICs and hardware Trojan insertion. So consider Alice asked Bob to design a circuit that compute a function f of x. So Alice, she can use these circuits to authenticate the username password pair of x and f of x, where x is the username, f of x is the password. So user will enter the username and password, and Alice can use the circuitry to compute f of x and then trying to compare and then see whether this user entered one is the valid or not. So now let's see Bob gives Alice this design for a very simple case when f of x is x squared and we have 10 potential users. They have IDs from 0 to 9. So this is the system that Bob designs for Alice. So we have this black box, implement the function f of x. And then Bob says that because you have 10 different users, so I need 4 bits to encode these different users. For example, user number 0 will have code 000, user number 3 will have code 0011, which is the binary representation of 3. And in terms of output bits, so Bob says that since you are doing fx equal to x squared, so the largest number you could get is 81. And for me to encode 81, I need 7 bits. In this case, 81 will be 1010001. And Bob tells Alice that inside this black box, all he implements is the square of x. And Alice can actually test by putting these 10 different values and then see what will be the output, and then can show that the system does no less. And how about the no more part? So we start from saying what is the exact design requirement in this case. So this is a huge truth table here. Start from the middle 2 columns with colored in blue. We see the input x goes from 0 to 9, and we see the required output x squared going from 0 to 81, which is the square of 9. And for each particular input, we want the output to be the square of the input. So what Bob does for the system is he's using a 4-bit binary encoding for the input, and he's using a 7-bit encoding for the output. And from this very simple truth table, we do see a couple of simple things. For example, the most significant bit of the input happens to be the same as the most significant bit of the output. So in that sense, we can define Z1 to be exactly the same as X1. And also the last bit or the least significant bit of the output, Z7, will be the same as the least significant bit of the input X4. And finally, we realize that the sixth output signal, Z6, it is a constant 0. So in some sense, when we do this design, what Bob needs to design is actually only four output functions, Z2, Z3, Z4, and Z5. So before we move on to talk about this, so let's see, give you a small hint for one of the early quiz questions. So remember, we want to do a square of x, or if you talk about in general, I want to multiply 2 numbers, x and y. And both numbers goes from 0 to 9. So in terms of the number of inputs, for each operand x, I need 4 bits, as we have discussed earlier. Because with 3 bits, I can only encode from 0 to 7, 8 different objects. And here I need 9. So if I have 2 inputs, x and y, and I need 4 bits for x, I need 4 bits for y, so in that case I will need 8 bits. And for the output side, the output in this case x squared goes from 0 to 81. So we know the largest number will be 81, and as we have discussed earlier, I need 7 bits to encode 81. So in this case, the number of output bits will be 7. So of course, in this case, you can argue that I don't really need 7 bits, because you see that the number of different outputs will be only 10 different subjects or 10 different values. So I could use as few as 4 bits to represent these 10 different values. However, the problem of doing that is with these 10 different values, if you use only 4 bits, you do not see exactly the values of this output in binary. So that is why we are saying that even Z6 is a constant 0, we still need the output bits to represent it. So in that sense, we have 7 bits as output. And finally, in this case, since we have 4 bits as input, with 4 bits, we know that we have a total of 16, which is 2 to the power 4 different input combinations. And in this case, we only care the first 10 of them. So the other 6 from 10 to 15, they will be the don't care conditions, which means in this case, we have 6 don't care conditions. Okay, let's come back to talk about the trusted ICs and the hardware Trojan. So what is inside the box of what the Bob's design? So Bob claims that he does exactly fx equal to x squared. And if we open up the box, we can see a circuitry like this. Or you may see a circuitry like this. And just to try to be honest, if you can see the difference between this circuitry, raise your hand. Of course, I'm joking. I mean, I wish I could see, but I cannot see your hands. So if I show you one more time, you see what is the difference here is take a look of this part and the functionality of Z2. This is the first design where Z2 is the product or the end of X2 and X3. And this is the second design, which we have changed the Z2 to X1 plus X2 times X3. And the signal X2 plus X1 comes from this OR gate. So let's show it again here. So to these 2 spots, take a look at that, and I'll show it again. So this is the original one, and then this is the second one. So apparently, these are 2 different designs. So what we can see here is, in addition to their difference, we see that they have the same number of gates, because I never change anything except I change the connection here. The first one connects this way, and the second one connects this way. So they have the same number of gates, and they have the same number of different type of gates. And moreover, they have almost identical layouts. The only tiny difference is the change we have here. So let's see what are the difference between these 2 designs. So what Alice can do here is, starting from the first design, he can verify that whether this design does exactly what she wants. She can plug in, for example, 0, where all the x1, x2, x3, x4 will be zeros, and then plug in all these equations, and then figure out that z1 equal to 0, z2 equal to 0, z3 equal to 0, z4 equal to 0, because you have a z4 equal to 0 here. And these z5, z6, z7, they are all zeros. So with the input 0, it does output 0. And as another example, if input is 1, where x4 will be 1, I can see Z7 will be 1, and Z6 will be 0, Z5 will be 0, and everything else will be 0. So that means that if input is 1, output is also 1, which is the square of 1. So Alice can confirm with all these things with 10 different input values. So what is important for Alice to prove the trustworthiness of this design is what more the system does. So what Alice can check is what happens if I give 10, which is 1010 into the system. And according to this definition of the output signals, the system is going to produce 1000100, which is the decimal 68, which is not the square of 10. And as another example, if I enter 11, the output will be the binary representation of number 89. Okay. So this system does some more, but doesn't do anything, suspicious, because this output is not the square of 10, and this output is not the square of 11. In terms of this application, Alice wants to authenticate the user. So if user enters 10, the output is not 10 squared, so it's not going to be authenticated. However, once we move to the second design, we know that the only difference is on the output signal Z2. And with this new design, we can see that once we have input 0, 10 here, 1, 0, 1, 0, and output Z2 will become 1 instead. This is because x3 is 1 and x1 is also 1. So 1 plus x2, which is 0, times this 1 give us a 1. And similarly, when input is 11, this bit will also be 1. And if you remember how we do the conversion from binary to decimal, so this bit position, a 1 means 32. So if I add 32 to these numbers, 32 plus 68 give me 100. 32 plus 89 give me a 121. So these are not just the magic numbers, but if you take a look of this, and then if you think further, so this 100 happens to be the square of 10. This 121 happens to be the square of 11. So in that sense, in this second design, there's a backdoor. And this backdoor is embedded intentionally. So in this case, what we have here is both pair of 10 and 100 and 11 and 121 will become valid. So when Alice used this system to do the authentication, these two entries will be considered valid. And in that case, the second design, we can consider this as it has a hardware Trojan. It's going to allow user who doesn't have access to have access to the system. To summarize today's lecture, what we are going to do next will be hardware Trojans and trusted IC designs. For hardware Trojan, we have learned two important characteristics of them. So first, it must have intentionally addition or modification to the system. Second, this addition or modification must have certain malicious purpose. And for trusted ICs, we have defined trusted IC as the system has to do no less, which means it has to meet all the design specifications. Also, it will not do anything maliciously. And from this discussion, we know that for a system to be trusted, it cannot have Trojan. That is what we call the Trojan-free ICs. And finally, for us to evaluate or to assess the trustworthiness of the system, we have to make sure that the system doesn't have any Trojans, which we call the Trojan-free. So hardware Trojan detection is about how to establish trust or how to assess the trustworthiness of the system. And on the other hand, when we do hardware Trojan prevention, we're trying to prevent hardware Trojan being inserted into the system. This is in some sense trying to build trust into the system. And these two categories, hardware Trojan detection and hardware prevention, we are going to discuss in more details in the following lectures.